Okay, so thank you for the introduction. I hope the microphone is working. It's a great pleasure, of course, to talk at the occasion of José's 60th birthday. I thank the organizers for the invitation. So the organizers somewhat asked me to give some kind of a little overview of the work of José. Of course, I can only cover parts of it, and what I can cover is things which I'm also somewhat involved with, because otherwise I think maybe I wouldn't be competent. So I think to characterize the collaboration in short is, when I wrote my habilitation, I wrote lots of questions there. And the upshot is, meanwhile, I think José answered all the questions there. So that's the short story. So basically, I called it variations. To start with, I will say a word about José's PhD thesis. And then the subsequent variations are related to the habilitation thesis. Lots of things we have heard already today. So I can be short on things, even though I have written slides, but some of them can be gone through quickly. So to say, first variation is extend Arakel of geometry to Shimura varieties, and then the third variation is, so to say, the start, which we did for revisiting the geometry of Jacobi forms, which was to rest for about 20 years. And then the last variation, that's the main focus, so to say. That's maybe something new. I hope at least that finally there is hope to extend Arakel of geometry to mixed Shimura varieties. So the prelude is just to set notations, which you all know. I work with an arithmetic variety. I solely work over Z. Of course, you can do it over number fields. Take the generic fiber, and the non-curly X, the normal X, is usually the associated complex manifold or the associated complex object. Then we have the cover-dimension piece cycles. We have the relations. As a quotient, we have the piece Chow groups. And then we know that Gilles Soulet proved that the direct sum of piece Chow groups have the structure of a commutative and associative ring, the product being given by the intersection product. Initially, the proof was K-theoretical. In the meantime, using de Young's alterations, you can also use these alterations together with the deformation to the normal cone. For example, a reference is Weber's PhD thesis in Regensburg. Then we have the usual F infinity involution, complex conjugation. Stuff is defined over Q. We have the real P preforms and PP currents, as you know in the theory. And then you have the example of a smooth current, of a smooth PP current associated to a smooth differential form. You have the Dirac current, so to say, as the opposite. And then the definition, the analytic definition of the Green's function is given by the DDC equation. DDC, Gy, plus the Dirac current is a smooth current. And this then led Gilles Soulet to the definition of arithmetic cycles together, which come with a Green's function, the corresponding relations, and then the arithmetic Chow groups and the intersection product of the direct sum of arithmetic Chow groups, then again forms a commutative ring with appropriate functorialities. The point maybe to be made is that on the analytic side, the product comes with the star product, and initially there was a little flaw in the argument that the star product factors through the rational arithmetic equivalence, and this then was fixed by Walter Kubler, but this was a point basically which I think caught also José's attention, that maybe one should make another approach to Green's functions, so to say. This slide, just again for notational purposes, if I have a line bundle, equip it with a metric, I call the metric the metrized line bundle L bar. And the first arithmetic Chow form, as we saw it also in last talk by Jan, is then just the divisor of a section, non-zero rational section, minus log of the norm of this section for this smooth metric. Okay, so let's start with the first variation and look how José started to think of another approach to define Green's functions. So I do this a little bit in a more general setting, so to say, because it will be useful for the second variation. So it starts with a little bit abstract nonsense, so to say. But of course, at some point, we have to give life to this nonsense, so to say. So G star star is what we call a Gillet complex, which is a graded complex of sheaves of abelian groups over the heuristic site of sheaves over R, and giving rise to a cohomology theory in the sense of Schule, which has a list of about 10 properties, which are the natural properties for a cohomology theory to have. In particular, it should have a product structure, which is graded commutative and associative. And then the cohomology associated to this Gillet complex is given by the hypercohomology, which you see here, if I can make it here, which you see here. And it comes also with classes from the Chow groups. So then, as a next ingredient, we're not only dealing with Gillet complexes, but we use some more general object, what we then called G complex. This is the curly C, again, C star star, sheaves of complex of sheaves of abelian groups. And it has two properties. It's connected with the Gillet complex, so there's a morphism from the Gillet complex to the complex curly C. And the C and M's should be acyclic for all M and N's, which then allows to compute hypercohomology by usual cohomology of global sections. So this is just for notational purposes. Here you see the cohomology of this G complex computed via its global sections over UR. And then we need two objects. We need relative cohomology and truncated relative cohomology. Relative cohomology was on the board several times already. So it's just the abstract thing. You have two complexes, A and B. So A here stands basically for this complex and B for this complex, so to say. You make the simple complex out of it by shifting B by -1. You take the simple complex, and this gives you the relative cohomology. And a little bit more complicated, but most importantly, is the truncated relative cohomology. That's, as we will see, the tool where the green functions will be in. So these are pairs of A's and B's, where A is an n cycle of the complex A, and B is an element in the complex B, but only modulo boundaries. And you require that f of A, the morphism between the complexes, equals the differential of B, so to say. So this is the definition of this relative truncated cohomology. So then we keep on going and concluding the abstract nonsense, so to say. So we give ourselves a cycle which has a support, and then we define what a green object is. So it's going to be an element in this truncated relative cohomology to the degree 2p. So p is the codimension of the cycle. And it has the additional requirement that if you take the classing, which brings it to cohomology, then it coincides with the class of the cycle over the Archimedean plane, so tensored with R. So in other words, if you look at this definition, a green object is a pair of two things. So it's a y, an omega, and a g tilde. So the omega y is a 2p cycle in the complex C, basically. And the g tilde is an element in the complex to the degree 2p minus 1, but away from y, from the support of y, and only modulo boundaries, so to say. So when then the complex, the G complex has an additional product structure, you can show that this can be carried over to a product structure in relative truncated cohomology And this is the replacement of the star product on this cohomological level. So I've written out here the formula explicitly, but I think I don't need to go into detail. The point is just we have now a cohomological, or José had a cohomological way to interpret green functions and the corresponding star product, so to say. And then you can put this abstract formalism into arithmetic cycles, into relations and abstract arithmetic Chow groups. And then you can show if the G complex has appropriate properties, then, for example, that it has an algebra structure which is commutative and associative, then this abstract arithmetic Chow groups also form a commutative ring. And it also has appropriate functorialities once you have appropriate properties of the complex. And the point is, as I just indicated, that this gave an abstract definition of the green objects and allows for a more transparent proof of the factorization of the star product through rational equivalence, so to say. Okay, so this was the background, which is useful for later, but what now José did, so he constructed a concrete Gilles complex, which he called D star log, D star star log, or D log star star, so to say. And what he then does, let V be a quasi-projective smooth complex variety defined over R, then take the Dolbear algebra of smooth forms on V, which have at the compactification of V logarithmic singularities. And then to this Dolbear algebra, you associate the linear complex D star log of V star invariant under F infinity. And this gives, then you prove that this complex fulfills the properties that are asked for the Gilles complex, so this long list of properties. And then the main theorem is that in this way, this abstract nonsense theory, now filled with life with this D-log complex, becomes isomorphic to the classical theory developed by Gilles and Soulet. And here is the assignment, which brings you from one side to the other. Here is the Y, which goes to the Y. Here is the green object to whom you associate in the green function, so to say. Oh, so this was basically the first variation. And let's now go to the second variation. And this started, well, this had some kind of a, was kind of en vogue when Jürg, together with José, organized 2005 this nice conference in Barcelona at the CRM. I have found a picture, and you see that we have been quite young at the time. So I think there is José, right? And you see organizers here also. So anyhow, the whole thing started basically in part of my habilitation thesis when I tried there to do arithmetic geometry on modular curves. And I mean, there was a nice summary also by Jan. So I just wanted to bring you up to my notation. I take the upper half plane. I take x to be the quotient of the upper half plane modulo SL2Z compactified by the cusp at infinity. Let's be very concrete. Take a line bundle of modular forms of weight 12, a sectioned Eisenstein series E12, the Peterson norm, the hyperbolic volume form. I didn't care about normalization so much. So then the Peterson norm looks like this. And then you see if you take the local uniformizing parameter at the cusp infinity, which is called Q, which is e to the 2 pi tau, tau being the variable in the upper half plane, then if you rewrite the Peterson norm, it's just the absolute value of the modular form times log Q to the 12. And there you see that this at Q equals 0, you get this logarithmic singularity. And since when we look at Green's functions, we take the log of the norm of a section, it's clear that you have a log-log phenomenon floating around, and that's why you get a log-log theory later on. But the origin was that I somewhat gave this problem to Ulf Kühn, and he was then able, I stated it in this way, that classical arithmetic intersection theory, or the arithmetic intersection number a la Arakelov, can be regularized to the extent that you can also take into account line bundles of the type just described with logarithmic singularities at specific distinguished finitely many points. And then it was mentioned that we have this nice formula, right? Well, up to normalization factors maybe. But it turned out that you have this kind of phenomenon that the arithmetic self-intersection of the line bundle of modular forms is basically the degree of the modular forms bundle times the log derivative of this degree plus some constant, so to say. And this was, of course, a kind of a motivation to start to look around to generalize this theory to higher dimensions. Of course, we were unable to do this, and this opened then the program to what comes next. So to say, let me just mention the first part I already said, so to say, but the second part in higher dimensions, then there was the result by Jan Brunier, José and Ulf, which was just mentioned, that they extended this result to Hilbert modular surfaces. And there was also conceptual formulation of the corresponding self-intersection number, arithmetic self-intersection number of the modular forms bundle in higher dimensions, once you have a formalism, and appropriate by Vincent Maillot and Damian Rössler. So to say, just to name a few, more should be mentioned. But now let's briefly summarize what then has been done. Basically, we have in mind this abstract formalism. José provided a nice Gillet complex, but now you said the formalism has a flexibility that we can work with an additional G complex, and then we maybe get an appropriate variation of the first theory. So we have the notation as before. Curly X is my arithmetic variety over Z. X is the associated complex manifold, XR as before. I take local coordinates on X. Let D be a normal crossing divisor defined by this equation, Z1 up to Ck equals 0. So it's the product of the first local coordinates. D is the dimension, by the way, of X. And I let V to be the complement. And so did I skip something? No, this is just to keep in mind. And then I mentioned if you want to make a theory, you have to take into account log-log forms, log-log functions. And so we defined what a log-log growth function is. So it's maybe complicated, and there are variations of these definitions, but let me stick with this definition, that a function is called, has log-log growth of infinite order along the normal crossing divisor if the function and all its possible derivatives can be bounded in this way. You see in the numerator this log-log 1 over Rj. Rj is the absolute value of the local coordinate for 1 up to k. And in the denominator, you have these products there. And now we have to keep on going a little bit. So these are log-log growth functions. Then you want to have log-log growth forms. So this is the subsheaf of the sheaf of smooth differential forms on our V. So this open part in X generated as a subalgebra by log-log growth functions on X together with these differentials, so to say. So the differentials for 1 up to k, k was the defining number for the normal crossing divisor, and then for j equals k plus 1 up to d, you just have the normal differentials. And finally, we come to the definition of when a form omega on X is called log-log along D, so that's the crucial definition after these prerequisites. If omega itself, d omega d bar omega and dd bar omega all have log-log growth along D in the sense up above. And the resulting sheaf is denoted by curly E double bracket D, so to say. So this is basically the starting point, almost the starting point of defining the G complex. So of course we have also to take into account, as before, the locus where the Green's function produces its log singularity apart from the metric. So we have now two divisors, and we have to make the sheaf of differential forms that are log along one divisor and log about the D prime. So D you should see varying, the D prime you should see fixed. So this then comes finally to the promised construction of the D log complex. So we have in mind D log, the complex constructed by José in the thesis. We take as our G-leg complex, and now we want to make a D-leg complex. We fix D prime, our normal crossing divisor. That's the divisor where the metric gets log singular, so to say, of our line bundle, or the metric of the line bundle. And then for any open subset V, we make this construction, so to say. So we take the limit over all possible compactifications of V by D, and then take the global sections of these mixed forms, which are log along D and log along the fixed divisor D prime, with this additional requirement. So this you then, in this way you get a Dolbeault algebra, and this again feed into the linear complex. And now that's the envisaged complex. What's written here, D star of E star log double bracket D prime of V. And then we prove that this is indeed a D log complex. And I mean, this assignment provides a D log complex, and we denote it in this way, D star double bracket D prime star. And then, of course, now you can run the abstract machinery. You plug this new complex into the abstract formalism. And the nice thing is that you get nice arithmetic Chow groups, which have a product structure, which in particular allow a push forward to spec Z, or to the Chow group of spec Z. And this is basically the starting point that you could then apply arithmetic intersection theory to automorphic vector bundles equipped with the natural invariant metric on Shimura varieties of non-compact type. For example, it was useful in the CUDA program, so to say. So this one application, nice result I'd like to mention, Gérard's result in his thesis, where he applied this to generalize, so to say, Faltings's construction. So Faltings, when he proved the Mordell conjecture, had a line bundle which had log singularities at the boundary. And then he proved the finiteness result. And Gérard, using our formalism, then generalized this result. So he had X as above. He fixes a divisor, D prime, normal crossing divisor, takes a line bundle with a good Hermitian metric. I do not define details, but it's basically a log singular metric. You have to add a little bit. And then he proved this nice result that for any constant C, there exist only finitely many cycles which are supported outside of D prime with a bounded degree and bounded height, so to say. And I just, for the sake of completeness, put the definition of the height. So you have your cycle, you take your green object, and then you multiply it with the first Chern form to the appropriate power, and then push it to spec Z, so to say. So this was somewhat the first two variations of arithmetic geometry. And the third variation, I can somewhat be brief, but this was basically the starting point of what Anna Maria was talking about, because when we finished this program around 2005, 6, or 7, I don't remember precisely, I always ask José, well, what about the mixed Shimura variety case? And then we did some computations. We got some kind of calculated some integrals. They turned out to be finite, but things somewhat didn't fit into a formalism. And then at some point we started somewhat in the flavor what Anna Maria said, to revisit the program. I can be very brief on this because this was just the very starting point of the whole story, which triggered the whole thing, that you now really go to the universal elliptic curve, which lies over the modular curve. We had some level structure. And here is the gamma n is the principal congruent subgroup of sufficiently large level. Then we had this on the board in higher dimension, H cross C, modulo this Jacobi group, gamma n times Z2, the universal elliptic curve. And then you compactify it. And I just take the compactification by adding, so to say, the n-gon at infinity. You have the canonical projection. And let me just be a little bit specific about this compactifying divisor. So we have local coordinates over the cusp, say at infinity. So Qn is what's written up there somewhere, e to the 2 pi I tau divided by n, because I have a level structure. So I introduce this u nu, v nu, which make up the Qn. The zeta is, so to say, the coordinate at infinity for the second variable. So u nu to the nu plus 1 and v nu to the nu have to be zeta. And then we have a compactification by n-gons, and the edges of this n-gon are denoted by theta p nu, where the nu runs from 0 to n minus 1. And theta p nu is given by the equation v nu, this local coordinate, equals to 0, so to say. So now you can make a nice picture. And this was the geometrical background, and then the definition of the Jacobi form was somewhat implicitly already on the board. Here you have an explicit formula. You see f of tau and z is somewhat invariant under the obvious modular action and the elliptic action up to an automorphy factor, c tau plus d to the minus k, which is, so to say, the modular automorphy factor. And then the exponential on the second line is the usual automorphy factor, which comes, so to say, from the theta function side. The vector space of all such function is denoted by jkm of gamma n. And of course, the automorphy factor gives rise to a line bundle, which I denote by jkm n on the open part, so to say. And now, that's why I'm going a little bit into detail here. We have the invariant metric, which is given like this. You have f of tau in absolute square for a Jacobi form. Then you have this exponential factor, e to the minus 4 pi m imaginary part of z squared divided by imaginary part of tau. And then you multiply by the well-known imaginary part of tau to the k, which is coming from the modular forms part. But now the phenomenon which appears is, if you translate this, restrict this to an affine coordinate around the n-gon, so to say, then you plug in, by a change of variables, the variables u nu, v nu are introduced locally beforehand. And then you, of course, the absolute value will survive. And then you have two terms. You have a function which are called psi k of u nu, v nu. And then you have this kind of mysterious log times log divided by log plus log quantity, so to say. So the psi k is the not unexpected log-log growth, which, so to say, comes from the modular picture, so to say. However, then you discover here that this new additional function, log u nu absolute square times log v nu absolute square divided by the sum of these logs, that this quantity is more singular than log singular, so to say. And this basically explains what Anna Maria this morning says, that Chern-Weil theory fails, so to say, because this produces residues, so to say, when you calculate integrals, so to say, while the log-log thing doesn't produce residues. And this is the explanation for this phenomenon, so to say. So just brief, then we already started to heal this problem because that's what Anna-Maria explained. You look at the proper modifications of your elliptic surface, and then you introduce the B-divisor as it has been done this morning. Take an appropriate section and then take it back. So the point is, Anna-Maria explained, and it's going to be on the next slide, that these B-divisors will satisfy Chern-Weil theory. And the reason is, when you look at these residues, this was this miracle that we then, so to say, experienced when we did this at the time, that the residues get smaller and smaller. So the metric gets less and less bad, so to say. And at the end of the day, you can make the limit, so to say. And this explains basically these formulas, which were on the board in general, so the geometric intersection, self-intersection of the B-divisor of Jacobi forms equals up to some constants involving, not surprisingly, k and m times the degree of the modular forms bundle. And this relation was also on the board this morning. And last but not least, this formula, which I already explained and Anna-Maria explained nicely, that the B-divisor dkmn satisfies Chern-Weil theory in the limiting case. As I said, the reason being that the residues get smaller and smaller. So the point now was in the fourth variation to put hats on this, so to say. So, and of course, being more general, so to say. And that's basically, this was the warm-up, and now let's go into the fourth variation. And this is the stuff, basically, I initially wanted to talk about on the board, and then the organizer asked me, and then I had to, so to say, interpolate. So let's now go to the fourth variation. And so this really involves a few definitions, but thanks to Robin, some of the definitions have more or less already been on the board yesterday. So this will not be too heavy for you. So I stick to the notion adelic arithmetic intersections, even though we had a discussion about the justification of the use of the word adelic at this point in time, but let's accept it, so to say. And so we start, as before, with an arithmetic variety and its associated complex manifold with diff index R of curly x. I denote the Cartier divisors on curly x with R coefficients. And as usual, the normal letters like normal x and normal d will denote the induced objects at the Archimedean place, so to say. So as Robin, well, not exclusively you dealt with Archimedean places, you also dealt with other ones, but I will exclusively deal with, so to say, Archimedean places when I talk about my further stuff. So the first definition now is about Green's functions. So a Green function for the divisor D will be called smooth, basically, as you know it, or plurisuperharmonic, if the locally integrable function can be chosen, GD can be chosen in such a way that for any open subset and any local equation FD for the divisor, this sum GD plus log absolute f of d squared is smooth or respectively plurisuperharmonic. So I think this is an accepted definition. So then, of course, we arrive at arithmetic divisor, putting together D with Green's functions, and here the Green function is of smooth type. And then we have diff hat of x, the arithmetic divisors on x. And I think this was also somewhat mentioned yesterday, at least in one of the talks, the arithmetic neffness. If D is relatively neff geometrically, the green function is plurisupermonic type, and the height at every point is non-negative. Okay, so we have all this in place. And as Robin said, basically what I'm doing here, I'm trying the title also. I mean, it doesn't say it yet, but it will come in a moment. Basically, I'm somewhat giving a summary of the theory Yuan and Zhang have been developing, but in terms of divisors. Basically, I somewhat omit adelic line bundle notation. So now, as yesterday, one fixes a boundary on our X, together with a green function, which one assumes to be positive, and the boundary we assume to be effective, and then look at the complement, X minus the support of B, and the same on the Archimedean place. And then basically this was in Robin's talk, somewhat in maybe differently stated, but I look at the space of model divisors, model arithmetic divisors on U of smooth type, which is defined as this direct limit of arithmetic divisors on some proper modification. And Rxu, as I said, are the proper modifications which produce, when restricting to U, isomorphisms, so to say. So if you take a model divisor, it lives on some level. So it is in, there exists a pi, such you just have an honest divisor living on some x pi together with a smooth green function, so to say. Now the next slide is that you now play with the adelic divisors, with the model divisors and produce adelic divisors. So, well, we accept this notion we agreed upon. So we see the norm, which implicitly at least has been on the board yesterday, that the infimum of all epsilons, such that given a model divisor D, is bounded from the left and the right by epsilon times b, minus epsilon times b plus epsilon times b, and similarly for the Green's function. So this, in Yuan Zhang, is shown that this produces a norm on the space of model divisors, so to say, and then of course you can complete it along with this norm. And by definition, then elements of the adelic divisor, adelic arithmetic divisor, is nothing than the completion of the model divisors with respect to this p-adic topology. And in other words, an adelic arithmetic divisor is simply given by a Cauchy sequence of model arithmetic divisors. So model arithmetic divisor living on some proper modification of X, and then you have a Cauchy sequence which converges with regard to this norm we have introduced. So then, last but not least, one has to, in order to state the main result of Yuan Zhang, one has to have Neffness and integrability. This was also mentioned by Robin yesterday. So the Neff adelic arithmetic divisor is the closure of the cone of Neff model arithmetic divisor inside of the adelic divisor. So if you have a Neff adelic arithmetic divisor, it comes as a Cauchy sequence of Neff model divisors, so to say, and the Neffness was defined beforehand. And integrability is then just the difference of Neff divisors. So it has to be noted that all these definitions do not depend on U, depend only on U, but not on a particular choice of the divisor B. And now one of the main results in the paper of Yuan Zhang is that on the level of Neff divisors, if D is the dimension of X, if you take D tuples of Neff adelic arithmetic divisors, you have an intersection product in the usual way, which gives you an honest intersection number. And of course, by linearity, it extends to the integral divisors. So, as I said, Neff-adelic arithmetic divisors are approximated by corresponding Cauchy sequences of model divisors. And then the intersection number on the right-hand side on each individual index level. These are just the usual well-known arithmetic intersection numbers we have at hand. And then it is shown that this sequence converges. I mean, basically, just look at the diagonal sequence, basically, but one can show a little bit more generally. If you let n0 up to nd go individually to infinity, that then all these intersection products, this sequence of intersection products has a limit, and it converges to this intersection product of adelic arithmetic Neff divisors. So that's content of the paper of Yuan Zhang. It is then one interesting point in this paper that they mention in particular, looking at the modular space of abelian varieties, AG over Z, or modular stack, dimension G, equipped with the Peterson metric, as we had it in the one-dimensional case, that this is an example of an adelic line bundle in their terminology, corresponding to an adelic arithmetic divisor. But we have not seen a proof that it's integrable, and we suspect it's not integrable, so to say. We have a, so to say, an example which is close to this, and it seems not to be integrable. So then it was, of course, a question, since by the second variation, we developed an arithmetic intersection theory taking into account these guys, so to say. And then the question is, can one somewhat incorporate this theory into the Yuan Zhang's theory, so to say? In other words, can one, that's why the title, Generalization of Yuan Zhang's adelic theory, can one somewhat extend the definition, which is still here on the board, to the extent that it also might give an intersection product in the non-integrable or Neff case, so to say. So we got stuck on this for a long time, so to say. Maybe I say a word about this later, but then last fall I was visiting José in Madrid, and we were struggling, so to say. We had a nice excursion over the mountains from Madrid to the other side, to Segovia. Had visited this nice city, and I think retrospectively one can say it was an inspiring trip, because somewhat I think we were rewarded, so to say. So let's use, or let's have a couple more definitions, which I think are not too heavy for all of you. So a closed positive 1-1 form, omega 0, let's fix it, so to say. Then we have the notion for a function v, phi from v, an open subset in X to R union minus infinity. We call it omega 0 plurisubharmonic if phi is upper semi-continuous, locally integral, and the DDC plus omega 0 is positive, closed positive 1-1 form, so to say. And then the space of all such functions on X we denote by PSH X omega 0. And then we need to care about singularities. We call phi1 in PSH X omega 0 more singular than phi2 if phi1 is smaller than phi2 up to a constant. And we call them to have equivalent singularities if phi1 is more singular than phi2 and vice versa. This then allows one to speak of an equivalence class of singularities of such functions, which we denote by a square bracket of phi1. So this determines the singularity type of the PSH function. So now we have the function of PSH functions on X, omega 0 PSH functions on X. And let's fix the psi. a technical detail about having small and bounded locus, but let me sweep this under the rug to not make more even definitions. So let's just take an omega 0 PSH function on X. And let's take another one whose singularity type is worse than the one of psi. And we call them to have a relative full mass if the respective non-pluripolar products coincide. And the subspace of PSH functions on X, omega 0 PSH function of X, such that phi is more singular than psi, such that phi has relative full mass, is denoted by curly E. So these are notions which we learned, or which I learned from José, and we learned it together from reading papers of Darvas and his co-authors and other people. So there's one final bit to define in order to arrive at the main statement. So this is just a bookkeeping slide. We just now needed to do so. I can make a comment why we needed to do so. To need this, to extend this to d+1 tuples. So that's why we fix now not just an omega 0 as a smooth closed positive 1,1 form, but we take just d+1 of them. And then maybe it's not well readable, but this is a boldface omega, which is then the tuple of these d+1 omega 0 up to omega d. And correspondingly, we take the product of these PSH spaces. So PSH x omega is just the product of PSH x omega 0 up to PSH x omega d. And similarly, we do this for these curly E spaces. So if you take now Pj in one of these components, PSH x omega j, we take the vector of all the psi's, and we then make the definition that the curly X boldface omega boldface psi is the product of all these spaces of functions in PSH having full relative mass, so to say, accordingly. So this is just bookkeeping, that we extend this from one component to d+1 components. It's just, but the crucial notion is the notion of mixed relative energy, so to say. And so we start from a d+1 tuple of PSH functions on X, and a tuple phi of such PSH functions which are more singular than psi and having full relative mass. And we define the mixed relative energy, which is denoted by E index boldface psi of phi, as this quantity, so to say, again, non-pluripolar product. So I see here is, I think, a bracket missing, or maybe it got just swallowed in some way, but there should be a square bracket here at the end. Sorry for that misprint. So yeah, you take the sum k from 0 to d, phi k minus psi k, and then you take the ddc phi 0 plus omega 0 up to the index k minus 1, and then you omit the index k because that's taken care of here, and do the same with the size, so to say. So to be correct, but since I know that you deserve lunch at some point, I don't want to go into many more details. Basically, this definition is only meaningful when the singularity types of phi and psi are the same, and then you have to work a little bit in order to treat the general case, but would just be yet another slide, so to say. So let's just accept that we have this notion of mixed relative energy. So there's one thing to be said. Why do we have to go to tuples, and why can we work individually? The point is that if, maybe I should also add, I mean, this relative energy can be finite or can be minus infinite, so to say. Of course, the interesting things are the cases when this quantity is finite, so to say. And if you do this, if you read in Darvas, you have just, so to say, the one-dimensional setting of this notion. Then if you have two functions which have finite relative energy, and if you add them, the sum is not finite necessarily. And so we hope to be able to do the generalization of adelic arithmetic intersections by just doing it for self-intersection and then use, so to say, the binomial theorem to get the mixed terms. But unfortunately, this didn't work, so to say. So that's why I apologize that we had to do this kind of bookkeeping yoga and make formulas still a little bit more involved. And then we finally had the first theorem, so to say. Well, it's the only theorem which I show, which is maybe somewhat new, and which leads then to a crucial definition. So let's take two Neff adelic arithmetic divisors, so to say. So dj bar and dj prime bar, but observe they have the same divisorial part, they only differ on the Green's function part. And we take a sufficiently large reference divisor, ej bar, which is bigger or equal than dj bar, plus 2 times the boundary divisor. Then for Gij is, of course, the Green functions for Ej, and omega j, the corresponding smooth 1-1 form in the DDC equation for the Green's function, so to say. And then we introduce this phi j and phi j prime by just subtracting this Green's function for the reference divisors, and they will become, so to say, by more or less by definition, will become PSH functions for omega j. And then if we assume that phi prime is more singular than phi, we can relate the Yuan-Zhang arithmetic intersection numbers in this way, where here is the relative mixed energy, so to say. And of course, since we worked here with Neff divisors, both sides here, I mean, both intersection numbers are finite, so also the energy will be finite, right? And what you basically have to do, you have to show that the phi prime lies in this space, and then you have to rewrite the integral, but that's something which you're familiar with, because you have the same, if you take this minus this, intersection number, you know that since the divisorial part are the same, everything is swept into the analytic calculation, which boils down to an integral. And then you have to work with this integral and bring it back, well, that the integral which is left basically is then this quantity which is here on the board. So, but now you see how it continues, so to say. Now, of course, you can say, well, let's take an F divisor and let's this be maybe a more nasty divisor, but assume the relative energy is finite. And then we can take this as a definition, and this I have written up here. So this is somewhat the generalization, at least what we hope is the generalization, but you will see it indeed works. So I just take now one Neff adelic arithmetic divisor. Again, I take my reference divisor, the Green's functions, for this reference divisor, and the omega j's, and the phi j again is this omega j PSH function on x obtained from the Green's function Gj. And now I look at any tuple phi prime of boldface x omega, boldface omega PSH functions on x, so to say. And we simply and then put the Gj prime as this phi j prime plus the reference Green function Gij, and thus obtain this adelic arithmetic divisors, so to say. And then we define this intersection number of these divisors by the well-defined one. This is the F1 plus the relative mixed energy, so to say. And now, of course, you see the thing stands and falls, if you want, with the finiteness or non-finiteness of this energy, so to say. So when the energy is finite, of course, you have extended the energy, and of course it's to be hoped that you find situations where this is no longer nef, so to say, arithmetically nef, and then you have extended your theory. And that's now coming to the final couple of slides. So we then applied this. I mean, this was, you have seen my story, our story, so to say. We have seen what we want to do. We want to apply this to the theory of Jacobi forms, so to say, and put hats on the formulas Anna Maria had on the board this morning. So I now, for reasons of time, I'm cheating a little bit. I do as if we work over the modular stack. Of course, we have to work with a level structure in order to have a proper, proper schemes. I mean proper in the sense of proper, not mathematically proper. So let's say G denote the modular stack of PPAV abelian schemes of dimension G over Z. Then, we take the universal abelian scheme. We take the Hodge bundle. So this you're familiar with. We take the line bundle, which corresponds to the theta functions. So we take the diagonal, L, the pullback of the Poincaré bundle via the diagonal. This is my line bundle L. And then the line bundle of Jacobi forms is just, as we saw this morning, pullback of the Hodge bundle to the k times L to the m. So this is the line bundle of Jacobi forms, which you can equip with your invariant metric. We've seen it several times now. So now we have to invoke compactification. So we have the cone of symmetric semi-positive real matrices with rational kernel that Francis introduced yesterday. We take a admissal projective cone decomposition, take a corresponding smooth toroidal compactification, AG sigma bar, and do the same basically for the universal abelian scheme. We get a BG pi bar together with a projective map, and we metrize, as I have already indicated, or as we have already seen, omega bar and L bar. And now, so this is the second last slide, almost. So let D be the dimension, G times G plus 1 over 2 plus G, the Jacobi forms bundle metrized. And then the point is it gives rise to an adelic divisor. That's the statement, which has a well-defined arithmetic self-intersection number, even though you keep in mind that this contribution doesn't fit in the formalism of Yuan Zhang, so to say. Still, we get a reasonable arithmetic self-intersection number, this one. I have already said what's written down below. Maybe the, no, this is on the last slide. So the number can be computed, and not surprisingly, basically it works what I said. The intersection number of this adelic arithmetic divisor, dkm to the d plus 1, equals the one of the modular forms bundle, so to say, up to some, quote, obvious junk, so to say. And just 2 comments. So this comment, because we had in Jan's talk the discussion about computation of the arithmetic self-intersection number of omega, so to say. And when we had this formula, this gave me some hope, so to say, because it reminded me on Siegel's geometric proof of the volume computation of the fundamental domain. He makes 2 steps. One, he pushes it to the boundary, and then he projects it down below, because the boundary is the semi-abelian space, and then he pushes it 1 dimension lower, so to say. And this looks like the second step, so to say. So you go from the universal abelian down to abelian scheme to the abelian scheme, so to say. So the hope now is maybe we can find a way to mimic the geometric part of Siegel's proof in the arithmetic setting, the first part. And the last part is that we that's why it took us so long. We had a long time already in the TOEIC setting such results. But finally it worked, and our PhD student, our joint PhD student, Gary, will talk about the TOEIC aspects of what I talked about today tomorrow, so to say. So now I'm done. I wish you happy birthday. Wish you all the best, good health, continuous creative work, happiness in life. Yeah, we worked together for about 25 years, is my estimate. So when I visited you the first time, there were still pesetas, I think. Yes. So this is some kind of indication that's a long time ago. But I thank you very warmly for sharing mathematics with me and for solving all these problems that I was not able to solve myself. And well, I hope for a continuation of our collaboration. Thanks very much.